All right, let's get the show on the road in the interest of staying on time. Thanks to all the participants from CNMI and Guam and American Samoa. I see some of you are attending in a group session. Just want to remind you, don't forget to sign into the attendance sheet to make sure that you get credit for today's session. So this is session 5. It's the first of 3 sessions focused on collection systems. We're going to give an overview of collection systems as a whole, but we're going to keep the primary focus today on the basics and on gravity systems. In other words, those parts of the collection system where flow is determined by gravity, although we'll give a brief introduction to lift stations and talk a little bit about maintenance. And then in the next session, we're going to cover pumping and force mains, where we're using mechanical means to essentially push sewage uphill. And then in the third collection system session, we'll be focused on operations and maintenance. And that is actually going to be the one that is probably covers the most things that are going to be on the exam itself. This is going to be sort of a lot of background information, but let's talk about this sort of in the context of the Cert exams. As you're probably aware, there's actually 3 different operator certification tracks. There's the wastewater collection operator, the wastewater treatment operator, and then the specialized biological industrial waste treatment operator tracks for testing that ABC does. For the purposes of this series, we're focusing on the first 2, the collection operator and wastewater operator. And as we've said many times before, familiarizing yourself with the need to knows and the testing materials is really important and critical to passing an exam. I also want to point out that although a lot of what we're going to be covering over the next few days is more collection operator focused, there is quite a bit of overlap between the 2 in exams. And even if it weren't critical for the exam, I think it is critical for treatment operators to understand how collection systems work and are operated and are maintained, and for collection system operators to understand how the treatment processes work, because they're essentially 2 sides of the same coin, 2 parts of a complete system. And as we'll see over the next few sessions, actions taken or not taken in the collection system can really have a big impact on the treatment facility and how well it works. So for many of you, I think some of the stuff today is going to be review, but that's okay. Wanted to point out, again, the resources. We've got the need to know criteria. There's lots of sort of over-the-counter commercially available resources you can get from places like Amazon. These are 2 books that we use in preparation for these. If you don't have them, they might be a good resource to reach out and get. They're about 150 pages each. There's one that's focused on the treatment operator test and one that is focused on the collection system. And it's basically 150 pages of test questions for all 4 levels. So level 1, 2, 3, and 4. So it's a good resource to have just for the career, because as you go up in certification, this will be a really useful test prep. And the best part about this is not only does it have very realistic sample questions, many of them taken from old exams, but it also shows you where that material is in the source material and where to find out more information about the specific exam question. So if you get one wrong, it basically points you right to where the information is for you to study. A lot of that information, background information, comes from the Sac State Water program's treatment guides that we've talked about a couple of times, but it's a really nice sort of setup. You've got the need to knows, you've got sample questions, and then again, those sample questions point you right at the source material if you've got any questions about it. We've covered this before, but I'm just going to go over a little bit briefly just because they are a little bit different. So this is a collection operator sort of need to knows and content areas. And you can see there's a few more calculations in class 2 versus class 1. And you can see most of it is focused on collection systems operations and maintenance and lift station maintenance, security, and things like that. The treatment operator exam has a different set of criteria, but there are collection system related questions in there. They're just kind of buried in some of these other topics in the middle about equipment evaluation and operation and treatment and process monitoring. So the treatment operator exam is going to have fewer overall sort of collection specific questions on it, but they are still likely to be there. And again, it's really important to sort of know what's going on inside the plant and outside the plant. And part of the reason for sort of focusing on this sort of broad basic stuff is that there is often a difference between what we call things in a specific locale versus how they're referred to in the exam. Different systems are built differently due to local sort of typical construction conventions. Different parts of the system might be locally referred to by different names. So part of what today is about is familiarizing you with the terms that you're likely to see on the exam so that you know exactly what they're talking about when they ask a specific question, particularly if they use a term that's just not used locally. We run into that a lot over here as well. So again, review all those various study materials that you have. This session will be recorded. And just as a warning, we have a bunch of thunderstorms coming through here. So if by off chance I disappear, just hang on, I'll try to get back. And if for some reason I'm completely shut off because the transformer blows up, we'll just record the session and send it out to you. So what we're going to talk about today, some design basics terminology. We'll dig into slope and velocity because those are critical to making gravity systems work. We'll talk about pipe materials and joint types because those kinds of questions often come up on the exam, and often you are asked questions on the exam about types of pipe that you don't have in your local system that you might not be familiar with. We'll talk about installation, pipe bedding, backfill, service connections, that kind of thing. We'll do a brief introduction into manholes, give a quick shout out to maps and a brief introduction to lift stations and cleaning equipment. As I said before, we're going to go more heavily into those in the next two sessions. Lift stations are all about moving sewage uphill. That'll be covered in the next section where we talk about pumping and force mains, and then we'll dig heavily into cleaning and maintenance and operation specifics in the session that's going to happen 4 weeks from today. So with that, let's dig into some basic design elements that you're going to need to know about, even if your particular system doesn't even have all of these components, or maybe you use, like I said, different terms locally to refer to these components. You can kind of think of this next section as sort of those basic building blocks and specific vocabulary that they're likely to use on the exam. We got to move sewage from our customers to the wastewater treatment plant. We're going to be focusing on gravity sewers here. So this is kind of an idealized diagram. We've got a bunch of buildings. Those are little orange blocks. We've got a wastewater treatment plant down at the bottom. Typically, the pipes are going to get larger, obviously, the closer they get to the wastewater treatment plant because flow is being combined from various sources. So working your way from the individual customers, you're going to start with building sewers or service connections. Again, they're referred to differently in different places. Some places just call them sewer taps. And obviously, the point of these is not to move sewage from one house to another, but to move them to a centralized pipe, which is generally in the exams going to be referred to as a lateral or branch sewer. Where these are located kind of depends. Typically, they're in the streets, but my neighborhood in Albuquerque, all the laterals in my particular neighborhood are in the alleys behind the houses. So the mains run in the streets, but the branch lines run in the alleys behind the houses. Branch lines are obviously going to be bigger than the individual service connections because they're collecting flow from multiple service connections. Next step is going to be the mains that the laterals dump into. These are going to be sort of the next scale bigger because, again, they're collecting typically flow from multiple laterals or branch sewers. Mains then in turn empty into what are called trunk sewers, which are essentially just larger and larger pipes. And a trunk sewer is going to often move into something called an interceptor, which is kind of the main pipe going into the wastewater treatment plant. And that might be serviced by a lift station, depending on where things are located. Again, in a gravity sewer, we're essentially using slope and gravity and the topographical contours to move sewage downhill, but that doesn't work all the time. So sometimes you've got to pump it uphill and use a lift station to do that. So this is kind of an idealized layout of a gravity sewer. Of course, there are going to be parts of the system, sometimes entire neighborhoods, that are lower in elevation than the wastewater treatment plant. So we've got to pump the sewage up. That will be done using sort of the same initial infrastructure to collect the sewage, but then it'll get moved to a lift station. And then the lift station could, again, empty into another gravity sewer or into what's called a force main, which is basically just a sewage line that's under pressure. We'll cover that aspect much more greater detail in the next session. Today, we're going to focus, like I said, on gravity sewers. So a couple things to know about them. As I mentioned, pipe diameter is going to increase as you move from source to treatment facilities. Gravity sewers are not designed to be pressurized. In other words, they're not supposed to run full. They are designed to run at a maximum somewhere between half and 3/4 full at peak flow. And there's a couple of reasons for that. But the big one is that helps maintain aerobic conditions in the pipe, right? So you've got air up there, the bacteria in the pipe can do their thing without the sewage going septic, which is sometimes what happens when we have manhole backups and we lose that airspace. So the network itself is obviously going to be designed appropriately for the population that it's going to serve. But sometimes when they're first installed, they're actually oversized a little bit. So it's going to be designed for the maximum expected peak flow, but also when maximum population density has been developed. So in some growing areas, there's a tendency to overbuild a little bit to begin. So when you're thinking about the design piece, the maximum flow is going to vary from location to location. Here in New Mexico, for example, there's a marked difference between typical flows in rural areas versus urban areas. Out in the country, it's typically about 60 gallons per day per person, whereas in urban areas, for some reason, it's about 125. I guess city folks are more wasteful. But when that flow happens is pretty universal. Typical max flow is somewhere between 10 and noon, and that's when all of the water from our showers and breakfast and things like that, when folks are getting up and going to work, basically hits the system and moves its way through the wastewater treatment plant. So the plant itself, or the network itself, is going to be designed to handle the flow that's going through it, and the wastewater treatment plant is typically going to be designed to handle 2.5 to 3.5 times the flow that you're going to expect on a typical daily basis, just so that it doesn't get overloaded. Couple of terms to remember. The crown is the top of the inside of the pipe. The invert is the bottom of the inside of the pipe, and that's also sometimes used for the bottom of manholes. So just some vocabulary terms there. So we talked about gravity doing the work in gravity sewer, right? Ideally, we don't have any pumps here in these kinds of sections. And how fast the sewage moves through the pipe is determined by the slope of the pipe as it's installed, right? Water runs downhill, so we ensure that our installations have a little bit of slope to them to ensure that liquid moves in the direction that we wanted it to. If you've never calculated slope before, it's pretty simple. It's just rise over run. That's how I typically think of it when I'm thinking about uphill. If you're thinking downhill, you can just sort of think of it in terms of the amount of drop over the length of pipe. So if a 100-foot long pipe is 2 feet lower at one end than the other, that's a 2-foot drop over 100 feet, and the slope is 0.02. The feet cancel out. Slope is a dimensionless number. So in gravity mains, like the one on the left side there, we've got flow being determined by gravity and the slope. It's going to flow at different rates at different times, but the idea is that it's never going to be more than 3/4 full. If it pressurizes, you've got a blockage somewhere, and that's typically found when manholes start overflowing. But again, those force mains that we're going to talk about in the next section, those are designed to run full, and they're pressurized. And in those cases, the flow volume and velocity is entirely dependent on the pumps that we use and how fast they're running. So let's talk a little bit more about the relationship between sewer slope and sewage velocity. There is a really complicated formula called the Manning equation that engineers use to sort of figure out how fast liquid will move through specific kinds of pipe. But for the Cert exam, you don't really need to know that. You just need to understand the relationship and some key values. The Manning equation that looks at the cross-section of the pipe and how much water's in there and the material roughness and the slope and a few other factors. But for the purposes of today, we're going to focus on slope and velocity. This is a somewhat exaggerated cross-section example, but the idea here is we've got a bunch of buildings. Those little orangey yellow lines are the service connections, and the gray line is the main or the lateral, and the wastewater treatment plant is off to our left. And so in this example, the pipe is perfectly flat. And obviously that's not going to work, right? Water needs to go downhill. If there's no downhill, it's just going to all pile up in the pipe as we thing is not working here, as we flush and run water down the drain. And eventually it would fill up and block. And when we think about the relationship between velocity and slope, this kind of makes sense, because if there's no drop, there's zero slope, right? 0 over 100 is 0. No slope means no velocity. So, and then of course, steep slope would mean very high velocity. So the goal here is to dial in the correct slope for the pipe that you're talking about. And in the context of the exam, remember some key values. And it's also important to remember that, of course, sewage is made up of liquids and solids: water from the shower, food scraps from the kitchen sink, toilet paper, and various other things that go down the toilet. And all of that has to move through the plant. So again, no slope, nothing moves, everything builds up and eventually gets blocked. So we put some slope into the pipe. Water runs downhill. If we do it correctly, not only will the liquids run downhill, but it'll take all the solids with it. And a key value to remember here is something called scouring velocity. Basically, the idea being that if we set up the slope right, the pipes will more or less clean themselves. Not that you won't have to maintain them, but under normal circumstances, the solids won't settle out. It's called scouring velocity. It's the minimum velocity you want to have in a pipe, and that's 2 feet per second. That's a value you should commit to memory. It often comes up in exams. You know, what is the scouring velocity? Or they'll give you a number and say, is this above or below? So remember, 2 feet per second is the minimum value. The range that you're going to see in an actual system is anywhere from 2 feet to 8 feet per second. Typically not any faster than that. 2.5 feet per second is considered ideal, but again, as long as you've got that 2 foot minimum, you should be good to go. If, however, somebody puts too steep a slope in, a couple of things can happen. Obviously, if it's too shallow, things don't move. If it's too steep, things move too fast. And this can cause two problems, one of which is kind of counterintuitive. One, if it's too steep, let's say instead of a 2 to 8 feet per second, you've got somewhere like 10 or 11 feet per second. In addition to the sewage and other pieces in there, there's grit and sand and a variety of other things that are in sewage effluent. And at those high velocities, those can actually start to erode the pipe, erode joints, so you can sort of chew the pipe up from the inside out. Can also have negative effects on treatment and equipment because things are moving faster than they're supposed to. Another sort of counterintuitive outcome is that when there's high slope but low use, so not a lot of liquid moving through, the solids can actually separate out, right? There's just not enough liquid to hold the solids and they get left behind. So it's a little bit counterintuitive, but at values or velocities above 10 feet per second, you can have this weird situation happen where under low flow conditions, solids actually drop out of the water and back things up. So the ideal range, 2 to 8, 2.5 is kind of sort of the design ideal. Anything above 8 is bad and above 10 is really bad. So now we know that there's a relationship between these two values, slope and velocity. Like I said, you don't need the formula because there are tables available to show, designers and folks in the industry what kind of slope you need to get the appropriate velocity for different sizes of pipe. And this is an example right here. And the thing I want to point out here is that the smaller the pipe is, the steeper the slope has to be to get that velocity. So for a 4-inch pipe, you need to drop 1.2 feet or about 14.5 inches over a 100-foot stretch to maintain that minimum velocity. Whereas for a 14-inch pipe, really pretty large diameter pipe, you would only need to drop about 2 inches over 100 feet, so 0.17 feet. So these are tables that are available to you. But the important thing to remember is kind of the relationship between the two. Big pipe, you need some slope, but the slope is going to be lower than you need for a small diameter pipe. And if you actually have a chance to sort of get into your basement or get into the crawl space under your house and look at the plumbing in your house, house plumbing is set up the exact same way. If you look at a local plumbing code, the 1.5 and 2 and 3 inch pipe requires less more slope than the 4, 5, and 6-inch pipe that you might have in a house. So just to give you a visual of it, the bottom line in each of these diagrams is perfectly horizontal, and these are to scale. So you can see for a 4-inch pipe, the slope's actually visible if you were to look at it from the side. That's a 1.2 foot drop over 100 feet, whereas on the 14-inch pipe, that 0.17, it's visible, but just barely. So this is the kind of thing that where you might not even be able to see it if you looked in a trench, but that's what we use measuring equipment for. So just to kind of summarize some of these design considerations, the pipes are going to typically follow the lay of the land so that you can get the required slope without having to dig really, really deep. Our design parameters are typically 2 to 8 feet per second. 2.5 is kind of the sweet spot, but 2 is the absolute minimum, and it's referred to as scouring velocity, like cleaning velocity. Collection systems are going to be designed for that maximum expected peak flow once the maximum population has been developed. So again, system might be a little oversized when it's first installed. Per capita flow is going to vary from location to location. It's a good thing to know, particularly if you move from one system to another, what the typical flows are like there. But the timing is usually the same, somewhere around 10 or noon. And then again, there's going to be those peaking factors for the actual treatment plant. It's going to be able to handle a lot more than the wastewater system, collection system typically throws at it. There's some other considerations around design. Pipe sizes are also determined by the size of available cleaning equipment. Obviously, you wouldn't want to install pipe that you couldn't clean. You got to remember that, at least in the gravity sewers, you got to have that aerobic headspace to prevent sewage from going septic. The depth of sewers is really location dependent. Typically, they look for sort of 4 to 8 feet. So that the lift stations, when they're needed, don't have to be buried really deep, and that you don't have to use a lot of force mains, but they can be a lot deeper. When we had the sewer line in our house replaced, my house is about 120 years old. It's in an older neighborhood in Albuquerque, and we're down closer to the river, and the lateral that connects to my house is almost 15 feet below the surface. So it's one of those, mileage may vary kind of situations. 4 to 8 feet is quite typical, but it could be a lot deeper. But what is really important is that when sewer lines and water lines are in the same right of way, so they're in the same street, the sewer lines are always below and off to the side to prevent contamination. And if you think about that, that sort of makes sense. If you got a sewer line break, you don't want it leaking down onto your water lines. The typical standards are 2 feet vertical and 4 feet horizontal. But in some cases, like I said, my lateral is in the back in the alley. My drinking water is in the front of the house. So at my house, they're actually half a block apart. So again, these are some basic sort of general design characteristics. It's kind of important as an operator to know what the typical design specs are where you are working so that you can have an idea of what you're going to be dealing with. Again, there's going to be those differences, and different locations may have slightly different parameters that they look at. So for an example, in New Mexico, when they're looking at building standards, the range that the state gives you is 60 to 125 gallons per day. But I was looking around at different states, and in Michigan, when they're designing sewers for mobile home parks, for example, they go based on the home site, and they use 200 gallons per day as the design value. So again, one of those things you might not necessarily need to know for the exam, but for sort of general operational purposes, it's a really good idea to have an idea of what the specific design requirements are in your location. So now that we've got the basics in, let's move into some specifics about the kind of pipe that you're going to run into and joints. Again, you may have seen all of these kinds of pipe in your network. You may have only seen some of them. It all kind of depends on when your different parts of your utility were installed. But in general, what we're looking for when we pick pipe for sewages is sturdiness, so resistance to deterioration, the ability to withstand surface loads because they're typically buried in streets, resistance to things like root intrusion, and as a related corollary, their ability to minimize leakage, and of course, cost and service life are going to be really important. And that's great, to know if you're starting from scratch. But like I said, a lot of systems have been around for a while. You're going to run into typically lots of different kinds of pipe from various eras, unless you have a recently built pipe system. Um, so it's good to know the basics, again, about these different pipe materials, and most importantly, how the pipe sections are connected, because these are things that do typically come up on in exams. So there's sort of four categories of pipe that you're going to run into: metallic, concrete, clay, and plastic. Sort of broken down, you've got asbestos cement and reinforced and non-reinforced concrete in the cement category. For the concrete category, you've got cast iron and ductile iron, which aren't used very much except in very specialized applications. As the metallic options, you've got vitrified clay, which is kind of a category of its own. And then you've got fiberglass reinforced ABS, HDPE, and polyvinyl chloride options, all of which are different kinds of plastic that have different benefits and contraindications. So looking at asbestos cement, not installed typically anymore because of the asbestos issue, right? OSHA has restricted its use, and this is something you want to be very careful around if you're doing maintenance, because if you're cutting into this stuff, you're releasing asbestos fibers and they cause lung cancer. That being said, it was used for a time because it's really strong and it's really resistant to deterioration by most wastewater. The one thing that it and pretty much all metallic and cement pipes are susceptible to is something called crown rot. If you don't know what that is, remember the crown is the top part of the pipe on the inside. Hydrogen sulfide is a natural byproduct of the bacteria that are in sewage. And it's wet on the inside of a pipe. You know, if you've been in a manhole, it's really humid in there. And that hydrogen sulfide will combine with moisture that's on the top of the pipe on the inside, and it'll turn into sulfuric acid. It's very dilute, but sulfuric acid, given enough time, will eat through just about anything. If conditions are poor, sometimes older asbestos cement pipes will be very, very thin at the top and sometimes just collapse because the hydrogen sulfide and this sulfuric acid have just chewed right through it. Joints on this stuff are typically rubber gaskets and sleeves. When this was built, they basically just built these straight sticks of pipe, right? They're the same size on both ends, and you use a rubber gasket to make the joints in between them. Again, not installed anymore, but something you're likely to run into. The various kinds of concrete pipe are typically used for bigger diameter pipes and pipes that are going to be under significant loads because they're really strong, particularly the reinforced concrete, because there's, it's like in a building, there's steel inside the concrete to help support it. Super rigid, can really withstand high surface loads. Like other cement pipes, they are subject to crown rot. So what you might see is coal tar or epoxy or plastic linings on the inside of the pipe, coatings on the inside of the pipe to help prevent that. In our picture here, it's unlined, it's just bare concrete. But that you will see that and it'll be black or some color. The way these are stuck together, you can kind of see the two pieces of pipe that are there. They're oriented in different directions. The one in the foreground, that front end is the spigot. That's the narrow end. Around that will be a big black rubber gasket that slips into the bell end, which is the other end. And they're just basically put together and held in place by friction and the installation, and that's what forms the seal. The bells always face uphill so that the water runs over the seal and not into it, so it doesn't try to, the fluid going through it isn't trying to push the pipe apart. These have been around for a long time. The typical standard now is rubber joint gaskets, but in older versions and in some locations, you might actually find mortar in the joints or bituminous material, so like tar essentially, as the sealing material. But again, typically not going to see these in small diameters. It's mostly the big diameter pipe. Cast iron and ductile iron were used broadly at certain times in the past. Now they're typically only used in very specialized situations, typically for bridge crossings. And in some cases where lines are very shallow, there may be a section that is designed to have a ductile iron or cast iron pipe. They're typically rubber gaskets or mechanical push-ins. In really old installations, you might actually see lead joints, kind of like older house plumbing often has. Like if you look at older house cast iron plumbing, the joints are actually have lead poured in them to make that seal. So you're probably not going to run into this, but it's good to know and what it could be used for in the sort of the modern era. Vitrified clay, like I said, that's a category of its own. This was kind of the standard, particularly for house connections for a long, long time. If you look at the oldest sewers in Roman times, they were made out of clay, just sections of pipe that look very much like this, but just don't have the plastic gaskets. So the nice thing about vitrified clay is it's impervious to just about everything: acids, caustics, solvents, gases, you name it. This can handle it. The downside is that it's really rigid. It's subject to cracking from root intrusion, and you know, so it's got specific applications. It's not going to be universally used. You can see in the picture here both ends of a typical modern vitrified clay pipe. You can see at the bell end on the outside ring or the inside, there is a yellow gasket. That's a polyurethane gasket. The spigot end, you can see, also has polyurethane on it. And when those get pushed together, they form a watertight seal. So these, again, bell is going to face uphill to make sure that the water is going over the joint and not into it. And you're going to see these in some places, but in most cases, modern stuff tends to get built with plastic pipe of various kinds. So let's move on to plastic pipes. So we've got fiberglass reinforced pipe. The benefits of this is it's flexible. It's really corrosion resistant. May be subject to crown rot in some instances. This is relatively new to the market, so they don't have as long as studies on it. But put together the same way many of these other kinds of pipe are, bells and spigots with rubber gaskets. The downside of all plastic pipe is that it has a tendency to deform if it's not installed incorrectly or correctly. So if you have unanticipated loading, so it's designed for a certain load and you get higher loads than what it's designed for, or if it's not installed incorrectly, it can actually deform an oval and sometimes break. So that's kind of the downside of plastic pipe in general, but fiberglass reinforced pipe in specific. ABS pipe. This is like the black pipe you would see at the hardware store. It's made out of ABS. It's really flexible. It's resistant to almost everything that you can find in wastewater, although petroleum products can erode it. Typically, the joints here are going to be either the gasket bells like we've talked before, or they'll actually be solvent welded. So if you put in a sprinkler system using like PVC or ABS pipe, it's the same concept, just on a slightly larger scale. Because of the way the joints are made and the issues with deformation, like all plastic pipe, it requires really, really careful installation. Another kind of plastic pipe you often run into is HDPE. Super flexible. Again, it's plastic that's resistant to just about everything. But in this case, you don't use those bell and gasket joints. They actually thermally weld it. So they'll take sections of pipe, heat the ends, stick them together, and essentially make one long welded piece of pipe. Where you often see these are in small diameter, low pressure mains. For force mains, you'll sometimes see these as retrofits for house sewer lines because when they do pipe bursting operations, so they basically drag a cable with a big pipe burster on the end of it through an old, for example, clay sewer line, they can put a length of this in behind it and just drag it through and then connect it. So you're going to see these in a couple of different contexts, but typically it's going to be small diameter, low pressure sewers and force mains where you're going to see these out in the field as opposed to customer service lines. And then there's sort of the typical standard that we see all over the place. The sticks of green pipe made out of PVC. It's super flexible. It's resistant to just about everything in wastewater, just like most of the other plastics. We're looking at a bunch of the bell ends here. The typical bell and gasket joints, they just flip together with friction and get held in place. Small diameter pipes, again, PVC, it's the same stuff that you'd use in your house essentially, or in a sprinkler, it's the same kind of material. So you can use solvent to weld it, but for big diameter pipes, they don't. They use the bell and gaskets because that gives the pipe the ability to move a little bit and still maintain a watertight seal without cracking. But like all plastic, subject to damage from heavy loads, which is why we're going to talk about bedding and installation in a second. I've put together a little table for you of the different kinds of joints that are used for different kinds of pipes. So we've got asbestos cement or metallic pipes, reinforced and non-reinforced concrete, vitreous clay, fiberglass reinforced, ABS, HPD, DPE, and PVC. And you can see the most common option is a rubber gasket, bell, and spigot. So if you've got a question and you can't remember and you got to guess, that's probably your best option. But this is a table that is worth looking at because it'll help you both identify the correct answer on the exam, but also if you're out working in the field and you're looking at an installation, you'll be able to tell whether it's likely done correctly or whether somebody just bodged something together. So this will be in the slides that we present to you. So let's talk. Oh, and just before we go on, just to be sure about the vocabulary, that end's the bell. The narrow end is the spigot. It's usually chamfered so that it'll slide into the other one very, very easily. And then that's the gasket. And again, the bells always face uphill. So let's talk a little bit about installation of all these different kinds of pipe we've been talking about. Couple critical things to remember for this. One being that you're always going to have some sort of bedding. It's really critical for the installation that the pipe be sitting on something that is specially prepared, that is angled correctly, and that is compacted. You throw a wastewater pipe or a drinking water pipe into a ditch with rocks and stuff in the bottom. Over time, it's going to move and it's going to break. So bedding is really, really important, as is the backfill. So backfill is bringing the trench up to the surface, right? Putting all the dirt that we dug out to make the hole in the first place back in place has to be done very specifically. Typically design specs or instructions from engineers will be very clear about how the bedding's supposed to be compacted in lifts or layers, because you can't just throw 8 feet of dirt into a hole and compact it on the top and expect that to work. It won't, so you end up having to compact in layers. And there are specific standards for different kinds of pipe and different kinds of soil. So we don't get into the specifics, but know that you're going to have to compact in lifts. Of course, how things are installed is going to be largely dependent on the components and materials that you're installing. But some general things about installation, typically it's going to be in excavated trenches. You're going to dig trenches from one end to the other and pipe is going to be laid in those. There are a ton of safety rules around excavation. Every year people die because they skirt the rules, don't use the appropriate shoring, things collapse on them, and bad things happen. So it's a good thing to read up on. This is an area where OSHA has rules for a reason. I think we have a safety training later on in the schedule where we'll talk about some specifics, but just generally know that going in holes is dangerous. There are a lot of rules, and make sure that you're following all your safety guidelines. Typically, when you are digging, if you run into something, it's a you break it, you buy it kind of situation, right? Here on the mainland, we have one call. I'm not sure whether an equivalent thing exists in the territories, but the idea is there are a lot of different kinds of utilities that are buried out in the streets. And when you're going to go dig holes, you want to make sure that the other utilities have an opportunity to come out and tell you where their stuff is so that you don't run into it, so that you don't accidentally, tear up a fiber optic cable or hit a gas line, or as in, put a telephone pole through your sewer or something like that. Typically, it's 48 hours notice. Again, this is something that varies by jurisdiction a little bit, but this is more from a practical day-to-day operations issue than the test exam example. But you're typically going to need some 48-hour notice. And again, it's one of those things where it's you break it, you buy it, and not only is the company that did the damage liable to be on the hook, in some cases, the person doing the digging can actually be personally liable. So when in doubt, ask. Good thing to pay attention to. Most sewer excavation is really deep, so it's atypical to be sending out crews with shovels, except under small situations where there's not a lot to be dug up. Most excavation is going to be done with backhoes, That being said, those trenchless technologies I talked about, pipe bursting, things like that, doing pipeliners, horizontal boring, it's becoming more common. I'm not sure how common that is out in the territories right now. Usually excavation is the cheaper option, but sometimes it's just not practical because of existing infrastructure. So they'll go with these other options. So you don't have to know a lot of specifics about these, but to know that they exist is important. And as always, follow the instructions for the materials that you're working with. And again, pay attention to safety. Small diameter pipe, the plastic pipes that are, less than 10 inches. Usually those can be moved around by hand with a couple of guys, but for big stuff, don't hurt yourself. Use machinery. And once again, bells need to face upstream. So let's talk a little bit about specifics of bedding and backfill, right? So rule number one is pipe has to be bedded. There are certain circumstances where it's installed without bedding, but you have to be really, really careful. So typically, the idea is that you'll dig a trench, they'll put specific bedding material at the bottom, use that to dial in the slope, compact it, and then install the pipe and compact around it. Typically, compacted crushed rock aggregate is what's going to be used, assuming it's available. You can use things like sand and pea gravel if they're compacted, and of course, how much you compact and how thick the layers are that you compact is again going to depend largely on the material that you're using. But just know you can't just put the pipe in and throw the dirt in on top. If just native material is going to be used, in other words, there's not going to be any crushed rock bedding, you're going to excavate a trench and lay the pipe in the ground, which does happen on some occasions, and sometimes it's the appropriate thing to do. It's just really important to make sure that that slope that we're trying to dial in is excavated correctly, because it's, the bottom of the pipe or trench is going to determine the angle that your pipe's on. So you want to make sure that if you're just using native materials, that you do that very, very carefully. Compacting is super important, particularly with plastic pipe, but really with all pipe. You don't just compact the trench bottom to support it, but you have to compact the sides around the pipe, because all the load is going to be coming from the top. And if the sides aren't compacted, you have to run the risk of the pipe cracking if it's a rigid pipe, or deforming if it's plastic. And compacting directly affects the amount of load that a pipe can carry. So if you're putting pipe in a street that cars are going to be driving across and things like that, it's really, really important to make sure that things are done correctly so that you don't have to effectively redo it. That being said, it's really important to remember that, with like HDPE pipe where it's butt welded, it's all the same diameter, right? So you could effectively lay that in the bottom of the trench and you'd be good to go. But if you're using, for example, PVC or one of these cement pipes that have bells and spigots, the bell is actually bigger around than the rest of the body of the pipe. So you have to account for that. And at every joint, there has to be a little extra excavation to make room for that bell at the bottom, so that the pipe isn't canted up and sitting on that bell, because you don't want it to break. We use the backfill basically to prevent the pipe from moving and getting broken or crushed. You're going to compact in layers until the trench is full. And then once the trench is full, you'll restore to whatever the appropriate ground surface level is. Again, how many layers you have and how thick the layers are that you compact are going to depend largely on the material that you're compacting. So, and just to kind of illustrate, sewer pipe, typically round cross section, right? It's buried under the street, it's in the ground. You're going to spend a lot of time focusing on this compaction around the pipe. And the reason that you do that, again, loads are going to come from the top. And if it's well protected, the loads from the top are going to try to push out the sides, and there's nowhere for the pipe to go. So it just holds itself in place. That's what we're looking for. If it's correctly bedded, it'll retain that circular cross section under load. Because again, the flow is dependent on the pipe being installed the way it's designed. So that's a good thing. If, for example, we were sloppy and we didn't compact around the sides and there were voids there or something like that, when you got those surface forces, the pipe's going to move, and it's going to move into the open space, or it's going to move to where that soil isn't compacted, and it might deform under load, which again is going to potentially result in the pipe breaking, but at a bare minimum is going to change the dynamics for the fluid that's moving through it, and make backups and things like that more more likely. So, if you don't bed correctly, it's more likely to form under load, and that is not what we want. Of course, after it's installed, how the heck are you supposed to determine what's going on underground? It's anywhere from 4 to 15 feet down, maybe, and you use something like this. Which is a mandrel. It's down in the bottom. It's essentially kind of a pig that you would run a cable down the pipe, attach this at one end. It's set up so that it's meets the minimum design spec of the pipe, and you drag it through. And as long as it makes it through, you're good to go. If it gets stuck, you got a problem that needs to be fixed. This is kind of the old school way of doing it. A lot of times nowadays, they'll use CCTV as well to do this kind of activity. But the main point here is to do the install correctly so that you don't have to do anything again. So looking for round pipe, not oval pipe. Moving on to service connections, we're kind of working our way backwards up to the houses. They're basically very, very similar and follow all the same general characteristics that our main sewer lines do. They're going to be sloped downhill. The individual slope of these things is a little less critical, again, because you're just worrying about flow from a single house. Who is doing the service connections varies from jurisdiction to jurisdiction. Typically, it's property owners that are responsible for this, and licensed plumbers that are making these connections. The example there on the right shows you some, solid shoring because it's a pretty deep trench there. But the point here is that this is kind of the interface between the publicly owned part of the system and the privately owned part of the system. And you want to make sure as the utility that things are being installed correctly. Again, there is some vocabulary terms. Service connections get referred to a couple of different ways, and there are different ways to make them, which are also, again, kind of dependent on the design the engineers provided and also just the common practice in a given location. So there might be clamp-on saddle tees that are similar to what you might see on the drinking water side. There are insertion Ys and Ts, epoxy bonded saddle tees. Some places they just cut a hole in the pipe, stick the service line in, and use a rubber gasket that's like a wedge to hold it in place. A lot of different ways to do it, a lot of acceptable ways to do it. The main point here is that however it's done, that seal needs to be tight. It's an area where there's going to be potential leakage, either from the outside in or the inside out, and it's also a potential area for root intrusion. So it's got to have a really tight seal. It has to be done correctly. And the other thing is that you do not want the sewer line sticking into the main. So you're connecting the pipe, but the last thing you want is a 12-inch main with 4-inch or 5 inches of house sewer line sticking into it, because it just provides an area for things to get caught up on and to create blockages. So just know sort of the different types of connections that might be made, T's, Y's, epoxy bonded T's and wedges, and that they're not supposed to stick into the main. And they'll typically come in at the top, either straight down or at a 45-degree angle. Other sort of major component that you're likely to be asked questions about are manholes. So let's talk a little bit about what they are, what they're for, and where they are. They're going to be installed pretty much ubiquitously throughout the system in laterals and main trunks and interceptors, and they're there for maintenance and cleaning, right? That's when there's blockages, you go in the manhole, and that's what you use to clean. They are typically going to be found any place a sewer changes direction, any place there is a significant elevation drop, where pipe size changes, and at junctions. So they're typically going to be at cross streets, at the ends of sewers for clean out. And like I said, if you've got small pipe feeding into a larger pipe, that'll often happen at a manhole. They're almost never going to be further than 500 feet apart. The typical distance is anywhere from 300 to 500 feet. I've seen them closer to like 150 and 200 in some instances. And the reason for that is that you got to be able to have equipment get from one end to the other. And 500 feet is about the maximum length of any sort of mechanical cleaning equipment you're going to have. So again, as I said at the beginning, part of the design is based on available cleaning equipment. So that's one of the reasons why manholes are not going to be that far apart. A lot of different ways of building them. These like pipe have changed over time. Old ones might be made out of brick. Typically now they're either fiberglass or precast concrete barrels. what's typical where you're at may depend on what's available and what's easy to ship. Here in New Mexico, almost everything that's installed now is precast concrete. So they basically excavate the hole, they pour the base, and then they just bring in these precast, pre-made cylinders and stack them up to the appropriate height. Typically, you're going to have steps or a ladder to get into them. I'll show you a diagram in a second. But remember, particularly with the precast concrete and the brick, just like the rest of the sewer, they're liable to attack by sulfuric acid from hydrogen sulfide in the sewage. They can get really slippery. They can corrode. The rungs are often metal. You want to be careful not to hurt yourself when you're going to these things. Know the parts of a precast concrete barrel. So you've got the port and slope base, which is usually going to have channels in it. I'll show you a picture one in a second. Inlet outlet piping, where different pipes are coming in and out. Those have to be sealed because, again, we're trying to avoid having liquid go out or in at any of those breaches. Precast concrete barrels are typically, as you can see in that diagram here, they're sort of rings that sit on top of each other. Again, each one of those has to be sealed. There's usually a concentric or eccentric cone at the top so that you can climb in. There's going to be level adjustment rings so that when streets get repaved, you can readjust the height of the manhole. And then obviously there's going to be a cast iron ring and a lid at the top. At least there should be. Good idea to sort of memorize the parts just so that you can rattle them off. If you can, looking straight down into one, this is often what you see. So here we've got a smaller pipe at the bottom that's entering and joining into a larger pipe that's coming in from the right and going out of the top. And you can see those rungs there are pretty chewed up and are starting to deteriorate. Other important things to remember about manholes, they are confined spaces. Like I said, we'll do a safety specific training, but manholes are very, very dangerous. This is another place where operators die every year because they don't follow the rules. They're defined as confined spaces because they've got limited openings for entry and exit. They're not designed to be continuously occupied. And unfortunately, because there's sewage down there, deadly gases can accumulate depending on what's going on, particularly if you're going in for a blockage. CO2, sometimes oxygen, it's not that the gases are deadly, it's just that the oxygen's been displaced. And there have been multiple occasions of somebody going in to a manhole without doing a sniffer test, without the appropriate gear, collapsing, and then somebody going in after them to try and help them and them collapsing too. So we'll discuss that more in a later section, but just remember manholes are confined spaces. Entry is covered by OSHA regs. We'll get into some specifics later on in another session. But the New Mexico test, for example, covers OSHA regs. Most of the national tests have some amount of questions about OSHA regs kind of buried into their safety and administrative procedures. Almost finished here. Going to do a quick plug for maps. They are a great way to get to know the system that you work with. Get familiar with the as-built maps for your system. If you haven't, recognize that things change all the time. And one of the issues that systems run into quite often is finding out that the maps aren't current or the maps are lost, which makes it very hard to find things and do your job. So there's typically going to be two sets of maps that you might run into, and it's good to sort of look at the stamps and what they say. When a project is being constructed, there's going to be working plans that guide the construction, and most utilities have copies of these laying around. Those represent what they planned to build. The as-built, and they will be stamped and will be marked as built, are the plans that actually show you what went into the ground. If you're going to be working on a project and you guys are reviewing the design of something that's been installed, make sure that you're looking at the right one so that you're not focusing on something that may not have actually been constructed. The as-builts, those are the true record of, at least they're supposed to be, of where everything is actually located. It should say final drawings or something like that on there, but recognize, repairs are going to get made, things are going to get changed. And it's a good idea to work with management to make sure that those maps get updated one way or another. And sometimes that's just hand drawings on the as-builts. Other times it might actually be, full on CAD drawings and stuff. Point here is that maps are your friend. not having them leads to headaches, not knowing how to read them leads to headaches. And you can use those maps to really start to understand how a collection system is put together. You know, because the design, there's a lot sort of buried in the design itself. I told you we talk a little bit about lift stations. This is really more sort of preview of coming attractions in the next couple of sessions. Lift stations are going to be pretty critical. Most sewage systems have a lot of them in different places, particular areas where the terrain is relatively flat because you have a gravity system digging downhill, but eventually, you know, you can't dig down anymore because you either hit bedrock or it just gets too expensive. So you put in a lift station to sort of lift the sewage back up to a manageable level so that either gravity or force main can take over again. So, you know, basic cycle, they'll go in and go out. They can empty into gravity mains. They can empty into force mains. Dawn in the next session is going to cover, you know, design components, preventive maintenance, and things like that. Because as you saw at the very beginning, particularly for the collections operations test track, understanding lift stations and lift station maintenance is really, really critical. There's also going to be a big section on sewer maintenance and cleaning. Again, this is a topic unto itself. We'll talk about equipment. We'll talk about tools. AJ will talk about, you know, blockage types, manual cleaning, and things like that. We got a few minutes left. I'm going to run a couple of sample questions here and then let you be on your way. And then, of course, the floor is open for any questions. If anybody has any, I'm happy to stick around for a little while. So Valeria, you want to fire up the first question? And for those of you sort of working in a group, you can talk amongst yourselves, pick a choice, and then have somebody select what you think the right answer is. So first question, what kind of pipe typically use rubber gasketed bell and spigot joints, cast iron, PVC, reinforced concrete, or all of the above? We'll give you about 30 seconds. All right, so there are no wrong answers in this, but one answer is more right than the others. All of these typically use gasketed bell and spigot joints, but PVC, excuse me, all of the above. Cast iron isn't that common, but it does sometimes get used. So again, none of these were wrong, but all of the above was the correct answer there. Larry, can you skip question 2 and go straight to question 3, which is the slope question? All right, so this is a quick slope calculation question. So what's the slope of a pipe that has a 2.5-foot drop over 100-foot length? Simple equation. And share the results. So the correct answer is 0.025. Remember, it's drop divided by length. So it's going to be 2.5 divided by 100, which is going to be 0.025. All right, jump on to the third question. This will be quick. I'm going to give you 10 seconds to answer this. So what is scouring velocity? What's that minimum velocity that we talked about early on? Is it 2? Is it 2.5? Is it 8? Or is it 10? So yeah, it's 2 feet per second. 2.5 is sometimes considered the ideal, but the minimum is 2. Which kind of sewer mains are designed to be pressurized? Gravity mains, force mains, both of them, or neither? Again, this should be pretty quick. We're waiting for one more person. Perfect. Everybody got that right too. Yeah, force mains. Force mains are the ones that are pressurized, and you can just kind of, easy way to remember that is force mains use pumps and pumps pressurize. Awesome. So that's it for today. Happy to answer any questions if anybody has, or at least to try to. And then, of course, our contact information is up there. This is being recorded. We should have this available for you in a couple of days. You know, we're happy to answer questions via email as well. So thanks for attending. We'll be back in 2 weeks, same time, same channel. We'll be focusing on pumps and force mains. All right. I don't see any raised hands, so I will give you the rest of your day back. Thanks for joining us. Again, if anything comes up or you have any questions about any of the resources that we talked about, feel free to reach out. We're here to help, and we'll see you in 2 weeks. Oh, I do see some chats. Yeah, we will send the presentation as well. We'll export this as a PDF. Yeah, thanks for reminding me. We'll export this as a PDF. We'll send this out to all the participants as well. Like I said, you should have both of those in a couple of days.